previous lessons, we talked about the ideal gas law, which can be represented by the equation PV equals nRT. In this lesson, we're going to talk about kinetic molecular theory. This is a way to explain gas properties on a molecular level. Imagine a gas made up of very tiny particles. The pressure is caused by the tiny particles bumping off the sides of the container. These bumping molecules cause a force, and the wall of the container is the area. Pressure is defined as force divided by area, or force per unit area. Now, each particle of a gas has a certain amount of kinetic energy. The equation we use to describe this is Ke equals 1/2 mv squared, where Ke is kinetic energy, m equals mass, and v is velocity. The units of this are joules. In ideal gases, the kinetic energy of the system is conserved. What this means is that while the gas particles are bouncing around, none of the kinetic energy is lost or transformed into any other type of energy. We say that the collisions against the wall or against other particles are completely elastic. An elastic collision is defined as a collision in which no kinetic energy is lost in the system as a result of the collision. Though particles may transfer energy to each other, the total kinetic energy of the system is conserved. Now, we talk about temperature a lot. Well, what is temperature? Temperature is related to the average kinetic energy of a system. Average because any individual particle might be moving at a different speed. Kinetic molecular theory is based on 5 postulates. First, gases are composed of molecules that are in constant random motion, traveling in straight lines until they collide with other molecules or walls of the container. 2. Molecules in a gas are small compared to the distances between them. 3. Pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. 4. The gas molecules exert no attractive or repulsive forces on each other. The average kinetic energy of the molecules is proportional to the Kelvin temperature of the gas. And we can see this in graphic form if we use the Maxwell-Boltzmann distribution. In a sample at a given temperature, not all of the molecules will be moving at the same speed. Some will be going faster and some will be going slower. Some molecules have high kinetic energy and some have less kinetic energy. In theory, you might have a particle or two that are just sitting there. The Maxwell-Boltzmann distribution is a graph that looks like this. It shows the relative numbers of molecules in a sample of gas that possess a given speed. In other words, how many molecules in the sample at a certain temperature are moving at a particular speed. Notice that this is a probability distribution. Sometimes the y-axis is labeled number of molecules. Sometimes it's called fraction of molecules, and sometimes it's called probability or probability density. It's all similar information. How likely am I to find a particle going at this particular speed? And speed is what's on the x-axis. Let's take a look at this curve. This example is for oxygen gas at 300 Kelvin. The number of molecules is on the y-axis and the speed is on the x-axis. You can see that the molecules to the right of the peak are moving very, very fast, and the molecules to the left of the peak are moving much more slowly, and in theory you might have a few molecules that are not moving at all. If we heated this gas to a higher temperature, the curve would start to flatten out and it would shift to the right. Notice that we're still going to have some molecules that are moving very slowly. The average speed of the molecules will be faster. If we made the sample colder, the peak would get higher and the curve would get narrower and the distribution would shift to the left. Let's take a look at a simulation. We have two gases here, red one on the top and blue one on the bottom. And we're going to start by setting them both to a very cold temperature. And you see their peaks are about the same, and they have about the same number of particles in them, and the particles are moving very slowly in both. I'm going to leave the blue one alone, and I'm going to gradually increase the temperature of the red gas. If we look at the left-hand side of the screen, we can see that the red particles are starting to move faster than the blue ones. Now there are still the same number of particles total. Nothing's changed there. They're just moving faster. But when we look on the right, we can see that the curve is starting to shift towards the right, and it's starting to get flatter. Because remember, if you have a sample of gas, no matter how hot it is, there's always a probability that some of the particles are going to be moving very slowly or even sitting still. The area under the curve is related to the total number of particles of the gas. Regardless of the temperature and regardless of how far to the right or left the curve is, the area under the curve will always stay the same, as long as you are not adding or taking away gas particles. Since the area under the curve is related to the number of molecules or particles of gas, if we were to take some of the gas out, the curve would get flatter. Now, what happens if we change the size of our gas particle? At any given temperature, all gases are going to have the same average kinetic energy for their molecules. However, gases with heavier particles are going to have slower average velocities. And we might predict this looking at the equation Ke equals 1/2 mv squared. If we want to have the same amount of energy and we increase the mass, the square of the velocity is going to have to decrease, because mass is inversely proportional to the square of the velocity. In this diagram, we have several different noble gases, and they're very different sizes. Assume that they are all at the same temperature. We can see that although the average kinetic energy is the same, and that's because the temperature is the same, the average speed for xenon, a very large atom, is much slower than the average speed of helium, which is a very small atom. Now let's take a look at how kinetic molecular theory relates to the gas laws. We'll start with Boyle's law. Pressure is inversely related to volume and vice versa. If the volume decreases, but the temperature and the number of moles are held constant, the pressure will increase. What's happening on the molecular level? Well, the container becomes smaller and the molecules are squished closer together, but there are the same number of collisions, and there's less wall for the molecules to bounce off of. Force is the same, but the unit area is smaller. Since pressure equals force divided by area, the pressure will increase. By contrast, if the volume is increased, there are the same number of collisions, but they're spread out over a larger area, so the pressure will decrease. In Gay-Lussac's law, the pressure is directly proportional to the temperature. As the temperature increases, the average kinetic energy of the gas molecules also increases. There are more frequent and more forceful collisions with the walls of the container, and the pressure increases. Particles are going to hit the wall with higher velocity. If you decrease the temperature, the molecules slow down. If you keep the volume constant, there will be fewer molecules hitting the wall at any given time. The pressure will decrease. In Charles's law, volume is proportional to temperature. As temperature increases, there are more frequent and more forceful collisions with the wall. The molecules hit the wall with a higher velocity and higher energy. The volume must increase to maintain constant pressure, since increased volume will decrease the frequency of the collisions and the number of collisions per unit area to keep the pressure stable. If you decrease the temperature by cooling it, the molecules slow down. The volume must go down if you want to keep the number of collisions against the wall, or the pressure, the same. In Avogadro's law, in order to maintain constant pressure and temperature, if the number of moles increases, the volume must increase, because volume and number of moles are directly proportional. Likewise, if you were to decrease the number of moles, the volume will decrease. And this has to happen if constant temperature and pressure is to be maintained. With Dalton's law of partial pressures, the molecules of any given gas will still hit the walls of the container at the same rate, regardless of whether other gases are in there. The total pressure will be the pressure exerted by all of the molecules from all of the gases hitting the wall. In summary, kinetic molecular theory relates the macroscopic properties of gases to the motions of the particles in the gas. The Maxwell-Boltzmann distribution shows the relative numbers of molecules in a sample of gas that possess a given speed. All of the particles in a sample of matter are in continuous random motion, and the average kinetic energy of a particle is related to its average velocity by the equation Ke equals 1/2 mv squared.